What's up, class? Today I have one simple goal, and that goal is for you to buy what I'm selling. And no, I don't mean my kettle corn that I sometimes sell at the farmer's market. I don't do that. I'm talking about, is it really important for us to understand linear equations? When are we going to see this kind of a problem in the real world? And so I'd like to share with you a couple of examples that are pretty practical that might model linear growth or something close to that. Okay, so let's take a look at a couple of these examples. Today, you're just earning credit for taking notes. So if you are taking the notes today, we're going to do the first one together. I'm going to get you started on the second problem. And then, actually, we're going to do the first problem together. I'm going to show you another example. And then you're going to finish the second problem on your own. And you're going to do that in your notes, and then you're going to submit those notes to me for credit. So that's what's happening today. But today we're going to be talking about applications of linear equations. Let's take a look at a first example. Another teacher recommended this example to me. I think it was really great. So everyone's seen these, hopefully, in the hallways of the school. They are not like a normal water fountain because they do a couple things. First of all, they have the water bottle filler, which is not necessarily relevant here, but they do filter the water. So they have a filter that is actively processing the water to make it taste a little bit better. It also says, like, hey, if you're wanting filtered water like from a bottle, it has a counter for how many bottles of water you are basically saving from going in the trash by using this filter and refilling a bottle that you already own. So it's a cool little gadget for sure. So the problem says the LK water filter needs its first filter replaced after it processes the equivalent of 85,000 bottles of water. Now, I made these numbers up. I have no idea what they actually are. It's going to depend probably a lot on the quality of the water that it's filtering, but I just made up that number. On September 5th, you noticed it had processed 23,492 bottles of water. And on September 19th, you noticed that it had processed 24,076 bottles of water. How many bottles is that? How many bottles is likely to have processed by? Is it likely to have processed by October 1st? And how many days are likely to pass until it needs its filter replaced? A couple typos in there, my bad. All right, here we go. So when you're taking a physical problem and you are trying to express it on paper, the first thing that you want to do is you want to choose variables that are going to make sense for us in the problem. Now, the two variables in this problem that are being measured, go ahead and take a guess if you think you know what they are. The two variables are, like, if we're trying to predict, okay, so it says how many days are likely to pass till it needs its filter replaced. It also says how many bottles is it likely to have processed by October 1st. So the two variables that we don't know that are in our linear equation that has two variables, we'll call these x and y. Well, normally it's x and y, but x and y don't really have a whole lot of meaning in the context of this problem, so I'm going to use new variable names. So I'll have a horizontal axis and the vertical axis. Okay. Now, when you have a linear equation like this, typically the thing that you're interested in, the variable that you're kind of measuring or monitoring, it usually goes on the vertical axis. So the thing that we are measuring here is the number of bottles of water that this is processed. So y is going to be, I'm going to use capital letter B to distinguish from lowercase b, the y-intercept. So I'm going to say capital letter B is equal to the number of bottles of water. Boy. This machine has processed. And that is technically, since it's already started, since it was installed. Okay, so y is going to be represented by the capital letter B, which is the number of bottles of water this machine has processed. Okay, that's our vertical axis, the thing that we're measuring. Now, that is kind of dependent upon a lot of other variables. It could be like the temperature or something, there are a bunch of other things you could do. In this case, though, we're talking about time. We're talking about the number of days that have passed. So I will, since I used a capital letter there, I'll use a capital letter here. D is going to represent the number of days that have passed. Now, the problem is we don't know when it was installed. So we can't go from the very beginning. We kind of have to go from our starting point. So what we'll say is, let's let D represent the number of days since September 5th. September 5th was the first day that we checked. So we're going to say, all right, that's the first time we checked. So that's going to be our, that is going to be our kind of starting point for our graph. So D will be down here on the horizontal axis. And so what we have here is we actually have the 2 points that are on a line. Now we have to convince ourselves, is water bottle use linear? It's not going to be perfectly linear because, people aren't really there on the weekends using water. And, obviously there's summer break, but for the most part, I think a linear trend makes sense. If people are filling their water bottles and they get in the habit, people are probably drinking about the same amount of water each day, so you could see this gradually increasing each school day. Okay, fantastic. So now what we're going to do is we're going to name the 2 data points that we have. So remember, our data points are going to go D, comma, B. So the number of days that have passed since September 5th, comma, the number of bottles that it's processed. So our first data point would be on September 5th. So how many days have passed, or how many days since September 5th is September 5th? 0 days have passed, and the machine had processed 23,492 bottles of water. Our second point is on September 19th. Which is 14 days from September 5th. So we'll say 14, comma, 24,076. So 14 days after September 5th, it had processed 24,076. So basically what, the number of bottles that had processed had gone up. So this is time kind of equals 0 down here, right? And over time it's increasing. So we have 2 points in time. And so what we can do now is we can write a linear equation that travels through those 2 points. Now, in real statistics, you wouldn't just use 2. You'd want to get a lot of data points to fit a line, and I'll show you that in just a minute. But, this is still useful, and maybe it's helpful for us to predict. Okay, and in fact, the longer that you waited between these 2 points, probably the more accurate that your graph would be. So remember, we're going to write it in slope-intercept form, which is y equals mx plus b. Okay, but remember, our y's and our b's have changed. So really we're interested in, y is going to be represented by b and x by d, so on and so forth. But in order to do this, the first thing we need is the slope. So we'll say m is equal to, come over here, y2 minus y1 over x2 minus x1. I'm actually going to fit this to the size of the screen. Okay, so we are finding the slope right now. So now I can plug in my data points that I'm going to use. So we'll call this point 2. That is 24,076 minus 23,492 over 14 minus 0. All right, this looks good. All right, I had to go get my calculator. So let's do some math here. 24076 minus 23,492 is 584. So that's 584, and then we have 14 on the bottom. And this is our slope. So rather than leaving it as 584 over 14, let's write it as a decimal so we can kind of think about what's going on. Remember, what are the units of 584? That's bottles. And on the bottom we have days. So when we do the division here, you end up with 41.7. So on average, over this period of time, this means that this particular water filter is processing around 41.7 bottles per day that passes. So great, now we know the slope. We've taken those 2 points and we've made our calculation. All right, so now I'm going to plug that in, except remember I'm going to use B equals mx plus m is now 41.7 plus 41.7 times d, which is the number of days that have passed, plus b, our y-intercept. Okay, so normally we would just take a point and plug it in, and we can use either point, but you plug it in, do the math, solve, but right now you can probably recognize that we already know the y-intercept. This is where, it's where our starting point is, where time equals 0, and our y-intercept is just 23,492. On September 5th, which is our starting point, we had 23,492. That's our y-intercept. So we can actually just jump right to our answer here. And if you were to plug in this point, you'd do 0 for d, and that term would go to 0, and you'd get b equals 23,492 anyway. So yeah, I'll let you do that if you don't believe me. 20,492. So great, we've got our equation. Fantastic. So this is the equation of the line that models our current situation with bottles in our filter. Why is it doing that? I'm trying to select. Aha! All right. Now let's go to the next page. Well, now we get to answer the next questions. This is exciting. The next questions. It said, how many bottles is it likely to have processed by October 1st? Okay, so to get from September 5th to October 1st would be like 30 seconds. Let's see here. We'll just say, I think in class I used 20. So let's see here. 26. How many days since September 5th is October 1st? And if we included, so we did 19 minus 5 to get 14 here. So if we're including October 1st, I think that's 27 days. So the question here is, how many bottles by October 1? And really what that's going to be is capital D equals 27. So now what I can do is I can use my equation, and what we're going to do is we're going to take D equals 27 days after we first noticed, and we're going to plug that in there. So you'll get B equals the number of bottles that machine will have processed on October 1st, 27 days after September 5th, 41.7 times 27 plus 23,492. This equation is so useful. We can now go through and make predictions about the future. Technically, that's a little bit of a faux pas in the math world. We call this extrapolation, but we're going to break some rules today. Hope you guys don't mind. I've always been kind of a rule breaker. Pretty cool. Okay, so the number of bottles processed by this machine on October 1st, based on our, assuming it's the same rate continuously, will be this multiplied together. Let's do the math, show all the work here. These two multiplied together is 1,125.9 plus its starting value on September 5th. So over the course up till October 1st, it's processed 1,125.9 bottles. But remember, it already had this amount processed, so the total amount processed on October 1st by the machine will be 24,617.9 bottles. Fantastic. Amazing, 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 amazing. Okay, great. What's the next question? The next question says, how many days are likely How many days will likely pass until it needs its filter replaced? Now, I told you at the very beginning it needs its filter replaced every 85,000 bottles that it processed. And again, I made that number up. So how many days? So in this case, this is a little bit different. So in here, we knew what D was. We knew that you said October 1st, so that means that's 27 days after September 5th. But now I'm asking how many days are likely to pass. So now I'm saying basically we want to know how many days, and I'm giving you the number of bottles that's processed. So we have B equals 85,000. This is our point that we're plugging in. So we're going to go to our equation yet again, bring this down, and now 85,000 is going in for B. So we can ask our equation a question. The equation holds the key, right? So I'm going to go to here times D plus 23,492. And now I can solve for D. So we plug the number into the equation, we solve for D, and it's going to give us our answer. All right, so let's see here. Minus 23,492 minus 23,492. And you end up with minus 23,492. Great. Okay, so what this number means, 61508, what this number means is after September 5th, this, we subtracted here, after September 5th, this machine needs to process another 61,508 bottles of water, or the equivalent of that amount of water, before it needs its filter replaced. Because it's already done 23,000. And we know that it's processing 41.7 per day. So then I can use my equation solving techniques that we learned. 41.7 divide by 41.7. And now we can get an answer. Oh, wow. Amazing. It's a very large number. Okay. D equals 1,475.01. Okay, that is days. So 1,475 days after September 5th, it will hit its filter change. And you can always change it before then. Now this is useful if you're like the custodial staff or something and you're trying to plan like, hey, do we want to spend a bunch of money on replacing our filters, or do we want to spend that money elsewhere? Because sometimes money from a budget doesn't carry over between years, right? So if you got money you're trying to allocate, this is maybe a good tool for planning. Linear equations. Oh boy. Okay, so how long is that actually? Let's divide that by 365 so we get an idea. Oh boy. 4.04 years. And of course these are approximations, so I should be using the approximately. So it's around 4.04 years away before you need to change the filter. That filter is doing some serious work. Nice job, filter. Keep hanging in there. Okay, now we're gonna do one more, but before I do that, I just want to show you an example really fast. Another one that where this might be used. You don't have to necessarily write anything down. But another one would be like if you're planning and looking at someone's savings. So this is, I'm not going to make you guys do this in the class, but this is, I just want to show you. This is what's called fitting a least squares regression line. You would do it in any like introductory statistics course. It's very useful for making predictions on a data set. So if we highlight our data, so this person, I think I said his name was Billy in the slides, we're not going to get there, but basically he's writing down every month or every couple months, basically, he's saying how many months have passed since he first started, and he's saying how much money is in his savings account. So let's take a look at Billy's savings. Maybe he's saving up for a truck. Maybe he's saving up for I don't know, something, a lot of gummy bears or something, right? Like way too many gummy bears. So if you go to insert chart, our options pop up over here. And let me zoom in so you guys have a, oh boy. So that's not the right kind of chart. That's not the chart I was looking for, at least. Come on, computer. Whoa, whoa. Hang in there, computer. Dictionary, get out of here. Click. Oh boy. Here we go. Alright, so here's our graph. If we change our chart to a scatter plot, we get a bunch of data points. You can see these points do not lie in a line. So it's not like, yeah, these points don't lie in a line. But so what we can do, but you can see that it kind of looks like they are growing in a line, but there's a bunch of variation. Like maybe Billy, when he was saving, he went out to eat a couple more times than he usually does. Or maybe someone came in to Billy and it was his birthday and he got a couple checks from some people or something. So certain months he's saving more than others, but you can see this linear trend. Now savings is typically not linear. It's an exponential growth. But over the short term, it looks linear, so I think that'll be good enough for today. So if you go into the customize for the scatter plot, and I think it's in series, you scroll down, you can fit what's called a trend line. This is called a linear least squares regression line. What it does is it makes a line that basically describes the points the best. And if you come down here, use equation, it gives you the equation. This is slope-intercept form. This is what we were learning, okay? The language of lines in statistics is slope-intercept form. That's why I'm teaching it to you. If you want to try and predict what's going to happen for a data set, this is the language that's used. So that's why we're teaching it to you, okay? It's used in statistics. It helps people make predictions, helps you plan for your future. This is a very useful tool to have at your disposal. And so what we could do here is we could say, well, Billy didn't, at the 10-month mark, Billy didn't put any data in. But the line can be used basically to make a prediction about Billy's saving. And we can make a guess and say, oh, it looks like Billy was maybe right about, at the 10-month mark, Billy was right at about, I don't know, $2,800 in savings or something, okay? So somewhere close in there, 2,700, I don't know, 2,600, it's hard to say. Anywho, that's how you use a linear least squares regression line. You can plug in values into here and make predictions. Pretty awesome. Let's take a look at our last example. I'm going to help set it up. If you guys want to try and set it up on your own, please do. We're going to look at another similar situation to before, and I want you guys to take a crack at answering these questions on your own in your notebook. So I'm going to be looking for those, and I'll give you points if you've given it a try. So let me help you set this up first. All right, your car dealership recommends you have a major service on your vehicle every 30,000 miles. A month ago, you checked and noticed you had 63,498 miles on your vehicle. Now you have 64,852 miles on the vehicle. So a month has passed between these two times. And how many days will you need to get the vehicle serviced? And how many miles will you have your car? How many miles will you have on your car 3 years from now? That is one sweet looking rig right there. I'll tell you that much. Let's pop up here and grab blue. We'll mix it up. Okay, so you get, if you own a vehicle and it's new-ish, you want to take it in for a major service at 30,000, 60,000, 90,000, 120,000, so on and so forth. So this has gone in. We can assume it's gone in for its 30,000. It's gone in for its 60,000. So its next check is at the 90,000 mile mark. So we need to create a linear model for this situation. So the first step here is deciding what our x and y, what we're going to call those things. So our x variable, I guess first decide on your y variable. What's the thing that we're measuring, that we're trying to predict? That would be the number of miles. And not to be confused with slope, I'm going to use a capital M here instead of a lowercase m. So we're interested in measuring the number of miles. So I'm going to say M is equal to the number of miles on the vehicle. This sweet ride. Look at that thing. Whew! Okay. So M is equal to the number of miles on our vehicle. That is, the thing you're measuring always goes on the y-axis, or the thing we're interested in. Miles is what we're counting. And then on our x-axis, we're going to put the thing that's kind of changing those miles. Now, is it reasonable for miles on a car to be linear? Linear means it's like basically a constant change every day. And I think so. I think it's also reasonable that you would do roughly the same amount of driving every single day. If you have the habit of going to work and then, going shopping, it's going to grow at roughly the same rate. So maybe weeks would be a better predictor than days, but I think days will be just fine. So let's go ahead and use capital D for days. So we'll say D is the number of days since, hold on. I don't like that. Number of days since. Now we don't have a date here, so I'm just going to say since you first checked your odometer, ODO. Your first day checked your odometer, number of miles on the vehicle. Okay, great. So here's D, here is M. What are our two data points? Okay, our two data points, the first one, and they're going to be in the form D, M. So in this case, number of days since you first checked. Well, when I first checked, 0 days had passed then, and the car had 63,498 miles. And then our second data point is a month later, so we'll assume the month has 31 days just for the sake of this problem. 64,852.7. So we have our two data points. So the first thing that you're going to need to do is you're going to need to make your linear model. So this is the first thing in your notes that you're going to want to try. I can help you with this if you'd like, but it's basically exactly the same as what we did before. You're going to use that equation, y2 minus y1 over x2 minus x1. Plug these babies in. And yeah, you're going to get 64,852.7 minus 63,498 over 31 minus 0. Let's crunch some numbers. That is 1,354.7 over 31. So if we take that number, divide by 31, we get 43.7. Now what's the units of our y? What's the units in the top? That's miles per units at the bottom day. So every day that passes, you're basically driving an average of 43.7 miles. That's quite a bit of driving. Maybe you got a little bit of a commute. That's okay. So our model then is going to be in the form y equals mx plus b, but remember we've changed what those things are, and remember we have a capital M that is really substituting for y, and then we have a lowercase m for slope, but our slope here is just 43.7. So in this case, our model is going to be capital M equals lowercase m, which is 43.7 times d, the number of days that have passed, plus our y-intercept. Well, our 2 points are like this, right? Because this is at d equals 0, so we know our y-intercept is going to be plus 63,498. So we have our model. Now, let's look at the questions that it's asking. So the first question, and then this is where I'm going to leave you to solve these. The first question is, in how many days will you need to get the vehicle serviced? Well, you need to get the vehicle serviced when the odometer hits 90,000 miles. So the first thing you're going to do is plug in m equals 90,000. Okay, when you plug in, this is question number 1. Plug in m equals 90,000, solve for d to get how many days until it needs to get serviced. And that will be days from the first time that you checked. The second question is asking us how many miles will you have on your car 3 years from now? Well, 3 years from now, let's assume it's 3 years from the time of service, so we don't have to subtract 31, but you really have to do that if you were talking about this time period, if this is now. Well, let's go ahead and be accurate, but it doesn't matter. 3 times 365, so 3 years from now. But remember, we got to subtract 31 from that because we're already 31 days past when we started. So you're going to plug in 3 times 365 equals that minus 31, 1064. So you're going to plug in d equals 1064 into this equation for the second one, and then it'll give you the mileage that will be on your car 3 years from now. So I hope this was convincing. I hope I've convinced you that linear equations have a purpose. Linear equations have a purpose, and they help us kind of make predictions about things that maybe we don't know, or predictions about the future. Typically, you want to stray away from predicting about the future, but it does help, especially. And one thing you have to know is there are many types of models. You can model all sorts of things and fit different equations and functions to data to make predictions. And that's how people are making predictions on, for example, the spread of the coronavirus. So thanks for watching, and I hope you guys learned something, and I hope you're convinced that linear equations have a purpose and are useful. Have a great day.